Now we're going to start on standing waves and the idea of superposition. Turn this over a little bit. Okay. Let's say you've got different waves coming across here. Maybe wave number 1. I've labeled the function for its displacement as a function of position and time. Displacement from wave 1 does like this. Wave 2 comes in here. Wave 3 and so on. Now, what happens where they meet? What happens if they overlap? Well, it turns out waves can move right through each other, which you know instinctively. I mean, light waves can cross. You shine 2 laser beams across each other. They don't bounce off of each other. 2 sound waves cross all the time. That's how you're able to hear people. When you have several people in a crowded room, maybe a bad example because it does tend to get confusing, but 2 people's speech doesn't bounce off of each other. Waves pass through. So where they meet, though, the displacement at any point where 2 waves or more are overlapping, the displacement at that point is the sum of the displacements of all the different waves that meet there. So the net displacement, d net, at that position in time, is equal to the displacement of the first wave at that position in time, plus the displacement of the second, the third, the fourth, and so on, which is the sum. Superposition, to superpose on them, just means to overlap them. If you've got a positive displacement for one and a negative for the other, you've got a positive plus a negative, there's a subtraction. If you have 2 positives, they're added, and so on. But really you're adding, and then the signs of these displacements takes care of anything that might be subtracted. Just add them all together, take care of the signs. Now, this gives rise to the idea of a standing wave, because they might not just be crossing, they might be moving in opposite directions. So what if you've got a situation where you've got one wave going this way, and then you have another wave with the same period, same frequency, same wavelength, same velocity, it's going to the same material, has to have the same velocity, and same amplitude, moving in exactly the opposite direction. Let's say we've got 2 waves on a string, and they cross each other going opposite ways, but they're otherwise identical. What happens in that case is they produce what's called a standing wave. What it looks like is this. Now, I've had to draw this in lacking colored chalk. I've got a solid line for what the total displacement looks like at one moment in time. Let's say that it's where they add up in such a way, you get a new wave here. And that's the start of our clock. Now, one period, both of these waves that are crossing have the same period, I have assumed. One half period later, it's flipped like this. And now what was up was down, what's down was up, and where they cross, they still cross. What you get then is this pattern that does like this. You don't see the pattern moving right or left. Instead, the pattern stands still. It just vibrates up and down like this. And you'll notice in particular that there are spots, evenly spaced out, called nodes. The nodes are places where the medium, let's say the string in this case, does not move at all. The amplitude at this point is 0. And here, and here. And the nodes, let's see, and in between the nodes are places where the amplitude is at a maximum. They're like this. Okay, things go from up and down, the nodes don't go. So these are the anti-nodes, meaning opposite of the nodes. At the nodes, there's no motion of the medium at all. Now, of course, the medium isn't moving left and right anyway. The waves might be moving left and right. The traveling waves are. Of course, the standing wave isn't. But the medium stands still. When I say no motion of the medium, I mean there's no transverse motion and no vibration in that case. So the amplitude is 0 here. The traveling waves are exactly out of phase at the nodes, so they completely cancel. If you've got a displacement this way, it's canceled out by a negative displacement down like that, of the same magnitude. This is called destructive interference. when they cancel each other out. And what you'll wind up with, since the intensity is proportional to amplitude squared, if the amplitude is 0, the intensity is 0. There is no intensity there in the nodes. The antinodes are regions of maximum amplitude, what's called constructive interference, where the waves, the displacement of one wave is up, the displacement of the second wave is also up at the same place at the same time. When this one's down, that one's down, so they add together. They build up to a greater amplitude. The traveling waves are exactly in phase. And this is called constructive interference, and you get your intensity is at a maximum because, once again, the amplitude is at a maximum. Now, the antinodes, antinodes are spaced out by half a wavelength. Now, I mean from, if it's up here, then it's down over here, but when it's down here, it's up here. What I mean is just the region square, that motion is at the maximum. That's the node. They're spaced out by lambda over 2, half a wavelength. And therefore, I'm just calling that a node. That's an antinode. Therefore, the nodes are also spaced out by half a wavelength as well. Okay. Now, you can see this, in fact, let's see. Before I do the mathematics of it, let me actually try to make one here. I think I've got a place I can put this up. Okay. Now, we don't have a pause button on this, so I've got to set this up on the fly. All right. We don't really have laboratory space in this room here. Now, this isn't the easiest one to see. You can see this big, giant slinky here, spring, moving. If I stretch it out a little bit here, all right. It's kind of tough to see the whole thing, but you can see there's a node where my fingers are. I'm giving it a little bit of motion here, but basically it's anchored so that it can't move. It can't move. There's no displacement, or very little of it. This is a node. The antinode, first antinode is here. Now, if you look a bit farther on, and I can't get to it, but it's in the field of view, you'll see another node there in the middle, and then you can't see, but where I've got it poked, there's another node over there. Now, if I do a little bit faster, this is true. You've got to get the frequencies out right. There we go. I'm having to do a little bit of spinning, but it gives the same thing. Now I've got more nodes and more antinodes, and I can't keep that up. Now, if I do it very slowly, I just let it go all up and down together and shake that vibration. There we go. Now I've got one node here and one node where it's anchored on the other end, and an antinode in between. And that's it there. Okay. Well, as fun as that is, let me get on with the actual sound effects. Okay. Let me... Oh, I've already got this written up. Excellent. All right, so what happens then? How do we make one? Well, there are a couple of different ways you can make a standing wave. One is you need the waves traveling in opposite directions through the same medium. You could have two sources, one here, that are in tune with each other. So you get the same frequency, wavelength, period, all that. Or you could have a single source here. It sends out a wave that then reflects off of a barrier. That's what I was doing. I was hooking that spring onto a barrier there, a hook, really. and it bounces off that end and comes back. And so then you wind up with this interference, constructive or destructive, how the waves interfere with each other. So let's imagine that I'm doing that. I've got one going to the right and one going to the left. So the total displacement is the sum of these two. And this is the principle of superposition, right here in action. So displacement of the wave moving to the right plus the displacement of the wave moving to the left. The displacement of the wave moving to the right, well, I write out the wave function, we call it, a sine of kx minus omega t. Now, I'm going to use lowercase a for the amplitude of each of the two waves separately right now. And that's only because I want to use capital A at this point for the total amplitude when they have interfered with each other. So, lowercase a sine of kx minus omega t. I've left out that phase constant phi naught right now, just because, well, I can pick whatever value for that I want to set the situation up, and I'm going to set it to equal to 0. Now, because of the negative sign here on the omega t part, that means it's moving to the right. Always that odd little thing, but the minus sign on the omega t means to the right, the positive x direction. A positive sign means in the negative x direction, or to the left. The wave moving to the left has displacement a sine kx plus omega t. All right, now, these two clearly have the same wave number, k. They have the same angular frequency, omega, and the same amplitude, lowercase a. I add those two functions together. I can factor out the amplitude a, because it's the same for both. Sine of kx minus omega t plus sine of kx plus omega t. I've got sine of something plus or minus something else. All of that inside the sine function. That is inconvenient. I want to get that out so that I'm not dealing with a sum or a difference inside the sine. You may remember, or you may not, there's a nice trigonometric identity here. The sine of angle alpha plus angle beta, phase alpha plus phase beta, whatever you want to call it, plus or minus there, is equal to sine of alpha times the cosine of beta plus or minus, match them up the same way, cosine alpha times sine beta. That then splits up the alpha and the beta so they're not added together, they're multiple. Well, they're trig functions multiplied. Let's do that. We'll use that. So this first one here becomes, I've still got the a outside, sine of kx times the cosine of omega t minus cosine of kx times sine of omega t. That's the first one, the wave that moves to the right. Plus, now I've got the wave moving to the left. Sine of kx cosine omega t plus cosine of kx times sine of omega t. Well, here, the cosine kx sine omega t appears here, negative there, positive here. That's gone. Life is simpler. Now I've got just this plus the same thing, so I've got 2 times a sine of kx times cosine of omega t. Now look what we've got. This is kind of neat here. Cosine of omega t depends only on the variable of time, t. That's the time-dependent part. The sine is just sine of kx. It has no time dependence. So this sine function here has a shape that stays the same over time. It varies only by position. This is position dependent. So I can group 2a times the sine of kx is constant with respect to time. And I can write that as a function, capital A of x. That's going to be called the amplitude function. It's how the amplitude varies with position along the rope that's being pulled or whatever. So the amplitude function, no longer a constant amplitude all the way across the string, but now it varies with position. 2a sine of kx. And now my wave function for the standing wave is the amplitude function a of x times the cosine of omega t. Very simple. How can we use this then? Let's take a look and find out where the nodes are in this kind of a wave. Now, hope that is easy enough to see. Might have to zoom in a little. Yeah, that's about right. Okay, where are the nodes? So let's use that wave function that we just got. The nodes are defined as the places where the amplitude is equal to 0. So I set the amplitude function, because it changes to x, equal to 0. I sub in what the amplitude function is, 2a times sine of kx. That's equal to 0. Now I can divide both sides by 2a. And I'm left with knowing that sine of kx is equal to 0. Now the sine is a varying function. What values of x make sine of kx equal to 0? Easy to do. You must know how to draw, to sketch out by hand, a sine wave and a cosine wave. Let's put it in terms of theta, the generalized phase angle theta. Sine of theta versus theta. So I draw this out here. And you can see that it crosses the 0 line here at theta equals 0, pi, 2 pi, 3 pi, 4 pi, and so on. So sine of theta is equal to 0. So sine of kx is equal to 0. Sine of theta is equal to 0 where theta equals 0, pi, 2 pi, 3 pi, and so on. How can I make that into a rule? Well, I can say it's integer multiples of pi. So I'm going to use m as an integer. M and n are often used for marking entities. So sine of theta is equal to 0, where theta is equal to m times pi. And m is 0, 1, 2, 3, and so on. By the way, it can also be negative 1, negative 2, negative 3, but we don't really even need to account for those right now. Okay. By the way, what was theta? It's the argument of the sine function, what's inside the parentheses. So that is kx. If theta is equal to m pi, kx is equal to m pi. Let me put it in terms of wavelength, though. We know that wave number k is equal to 2 pi over the wavelength lambda. So I sub that in here. 2 pi x over lambda is equal to m times pi. Cancel out pi. Solve for x, meaning where. That's a question of what is x when you're at a node. So that x values for the nodes are m times wavelength over 2. Now I've labeled this x subscript m, x sub m, because there are different values of x discretely changing, sharp changes, not a smooth change. So this is marking the individual nodes there with m, where m is 0, 1, 2, 3, 0 and positive integers, or we could say non-negative integers. M times lambda over 2. Okay. Now, given that, let's take an example. I'm going to give, this is an example in the book, a string with a certain linear mass density, a certain tension on the string, a certain frequency of the wave generator, and a certain amplitude, and ask how far apart are the nodes. Let me move this over here. All right, given a vibrating string with a density of 5 grams per meter, a string tension, T for tension, S for string, of 8 newtons, a frequency vibration of 100 hertz, and an amplitude, still using lowercase a for now, because we're doing the standing waves, of 2 millimeters, 2.0 millimeters. How far apart the nodes? Okay, we don't even have to go through all of that mathematics. What we need to remember is that the nodes are spaced out half a wavelength apart. So the node spacing is equal to lambda over 2. Half a wavelength apart. Okay. Now, I've got to put that in terms of something I can use. You may recall that the speed of a wave going through the material is equal to the square root of tension over density. So, and that the speed of the wave is also related to the wavelength. So this is an equation that will connect some of those facts with something that we have here. Let's see. V equals lambda F. Boxing that in because it's a report equation that you've already learned. That means to solve for lambda, because that's what we have, I divide by F, so V over F equals lambda, and I sub that in. Okay, now, what about the velocity? The velocity is equal to square root of T over mu, T sub S over mu. The S differentiates it from the wave period. And I put that in, okay. Now I've got to substitute in numbers. Okay. A little short on room here. Okay. So I've got a frequency, let's see, 1 over 2 times the frequency. The frequency is 100 hertz. I want it in terms of meters, kilograms, seconds. A hertz is 1 over second. So 1 over 2 times 100, 1 over seconds, times the square root of, turn the camera again, let's see, square root of. Now, the tension, yes. The tension is 8 newtons. What's a newton? It's a kilogram meter per second squared. So take these are sort of derived units, like a newton, a hertz, and put it in terms of the fundamental units. Meters for length, kilograms for mass, seconds for time. Okay, divided by mu, which is 5 grams per meter. Now, again, we gave it in grams, put it in kilograms. That means it is 5 thousandths of a kilogram per meter, or 5.0 times 10 to the minus 3. I did the conversion in my head. I guess that was easy enough. Okay, let's see. Kilograms divided with kilograms. Meters are the wrong place to divide out. They're actually going to multiply together. Here, I've got 1 over 1 over seconds is seconds, so seconds over 200 times the square root of, this comes out to be 1,600. I'm left with meters squared per second squared, all under the square root. This gives me seconds over 200 times 40 meters per second. Seconds and seconds cancel, and I'm left with 40 over 200. I'm left with 0.20 meters Or, in more convenient units, 20 centimeters for the spacing between the nodes. What about the amplitude at the antinodes? Now, what's the amplitude of the nodes? 0, by definition of a node. The amplitude of the antinodes is even easier. Take the amplitude function, A of x. It's equal to 2a times sine of kx. Now, lowercase a is the amplitude of the individual waves, traveling waves that are coming in. All right. At the maximum, well, 2 is not changing, a is not changing, but sine of kx is a function that changes with position. What's the maximum of the sine of anything? 1. So I know the maximum, that's 1. So, A max equals 2A. A is 2 millimeters, so I'm left with 4.0 millimeters. The constructive interference simply adds the two waves' amplitudes together. All right. Now, we'll take a look in particular at standing waves in a string. And the string that I had used there is pretty close to doing that. But it made it a little bit easier to demonstrate. Actually, before I even explicitly talk about waves in a string, I can talk about reflection and transmission somewhat more generally. And while the explanation I'm using is specific to strings, it'll apply generally for waves. Maybe I should mention that this is standing waves in strings still. Okay, so reflection and transmission at a discontinuity in the medium, meaning where the medium's properties change, a place where the wave speed would change as a result of that. This could be a boundary, it could just be a different density of the medium. All right, I'm going to give you 4 different cases here. The book only describes 3 of these, but it's important to know the 4. Let's say that we have a string with one end rigidly attached to a wall. That's massive, it's not going to move. Essentially infinite mass, so it cannot move. Now, when you have a single wave pulse, which is easy enough to describe without having to worry about all the rest of the wave, if you have an incoming wave pulse coming in like this, what happens when it hits that hook there? What winds up happening is that the wave can't move the hook. the forces as the wave is coming along here and it's trying to pull the string. Let's talk about the last molecule at the very tip end of the string. As it comes over here, the tension forces in the rope are pulling upwards on that molecule. We'll just look at the vertical axis now. Now, because it is rigidly attached, then the acceleration has to be 0, but if the acceleration is 0, the sum of all the forces must also be 0. Here's the second law. Sum of all forces is in A is 0, A sub 1 is. So there must be another force of opposite sign with the same magnitude that will cancel out the first one there. That is provided by what you might call a normal force of this hook on the tip end of that string of the rope. Now, the neat thing about that is that as that wave has gone on here, this normal force then creates another wave. It's giving a downward force to this that then sends out another wave pulse in the opposite direction. Of course, it moves backwards, and that's the only way it can move, but with the opposite phase. It's inverted of the same amplitude, moving the opposite direction and with the opposite phase, meaning if the initial pulse was pointing up, the outgoing pulse, the reflected one, is pointed down. Okay, so this is for a rigid barrier that the rope is connected to. Now, what if we have rather than a rigid barrier, this is a single example here, rather than a rigid barrier, what if we simply have a light string attached to a heavier rope? Or to make it less extreme example, a lightweight rope attached to a thicker rope. All right? So the density is lower here, it's higher here. What effect does that have on the wave going through? Well, one thing is, and this is what, it's not just the rope density, but in general, if the medium has allows the velocity higher over here, if the wave and pulse is coming from a region of a medium where it's got a higher velocity into a region where it has lower velocity, then what happens? It's almost like this case here, except it's not rigidly attached. Even though this material here, in the example of the rope, it's simply denser, heavier per unit length, and so it doesn't move as easily as this one does. It does move a bit. So you do get some of the wave transmitted. Now, what's going to happen is, let's say this is the amplitude coming in. The amplitude of the transmitted wave is lower, a lower amplitude, because not all of the wave's energy goes through. Some of it is, in fact, reflected. Now, the transmitted wave has the same phase, so it's pointing upward, if the initial one is pointing upward, but you also get a reflected part of the wave here. It is out of phase, it's with the opposite phase sign, moving backwards in the opposite direction. Now, the reason for this is that this reflected pulse that is inverted exists for the same reason that this one did. Here you have at the boundary, this doesn't want to move that much. It does move some, but not as much as this lightweight rope does, and so it exerts a downward force of greater magnitude that then sends the pulse back. But it does move some, so as it goes up, it transmits this on through, but more sluggishly. This then happens in general whenever you go from a medium of higher velocity into a medium that has a lower velocity. All right, now what if it's the opposite way? What if you start off with the pulse in a heavier rope or one that has a lower velocity? and then let it move into a material with a higher velocity, higher wave speed. You get an interesting thing happening. You do get, let's see, you do get a transmitted pulse. Notice that this transmitted part is not of that noticeably lower amplitude there. The exact amount of it, of course, depends on the ratios and swing speed and so on. But you also get a reflected pulse. But the reflected pulse has the same phase as the initial, the incoming pulse. It's not inverted the way the other one was. Apparently this one's also going uphill. That's just my drawing. Okay, because you've reversed the situation where now the force is on the tip into this one here. You've got a line of material that can easily transmit. It doesn't resist that motion as much, and it exerts smaller forces. The detailed explanation probably best solved using conservation of energy. It's a little tougher to do with the forces involved. And your book gets it all together. Now, let me give one more example, which is not covered at all in the book. It's kind of like the extreme version of this example. What if you have a rope of whatever density that then simply ends without a rigid attachment? Now, if really it were not rigidly attached, then when we do it, it's just going to kind of flop around. So let's say it's free to move vertically, but not flip around sideways as such. We've got a rod here and a loop, let's say a massless loop. Find those in the hardware store, I guess. It can move freely up and down, and the rod doesn't, that's the rod there, doesn't exert any other forces on it, just keeps it from moving sideways. Now, when this happens, you get back an identical pulse reflected with the same phase. So it's like this case, except because you're not changing the, there is nothing that is transmitted. It's all reflected, so the amplitude has to be the same. Conservation of energy. Remember the intensity, energy per time per area, is proportional to amplitude squared. So if the energy per time per area is the same, the amplitude has to be the same. All right. Now, explaining this might be a little bit easier than explaining that one there, but think about this as being attached to a rope of zero mass. And so as it does this here, as it's carried up, this rope doesn't have to transmit a wave gradually. It's like there's an infinite wave speed here. So as this loop goes up, this imaginary, invisible, massless rope moves completely horizontal. It stays in a perfectly horizontal line as it slides up and down. It exerts no forces back on this. Gravity, as this loop slides up here, gravity exerts a downward force. And as it comes all the way up then, and the wave has gotten on from here, gravity is pulling this back down now as the wave is passed, and it makes another wave in the other direction, but it's starting from up. So as it comes down, it's sliding it back out this way in the same shape, not inverted. It's actually a rather poor explanation. As I say, it's kind of tough to do from the standpoint of forces and Newton's laws alone. A bit better using conservation of energy, but well, I think sometimes it's easier to see at least some of these from the standpoint of what are the individual molecules doing. All right. So those are the four general cases. You will find, by the way, and if you do any work with, say, electronics, audio amplifiers and things, we'll get later on into the concept of impedance and impedance matching and electromagnetic waves, or the electrical signal, which makes a wave inside the equipment. And if you go from one conductor, one wire to another kind of wire, you get similar things happen. You get the electric wave reflected back when it should be all transmitted if you don't move it right. Okay, finally, I'm going to go through and show about the idea of harmonics. Leave the camera on that for a moment. Okay, so as we go for reflection, how do we use reflection in the string to create standing waves in the string? So recall what we had for the displacement in a standing wave. One-dimensional, I've got x here. The amplitude function, a of x, times the cosine of omega t. This is the time dependence. Where the amplitude function is equal to 2a times the sine of kx. Okay, putting that all in, we get that. 2a sine of kx cosine of omega t. Now, if I've got, let's say that the same example I gave with the spring over here before. I've got it rigidly attached to the other end. Of course, it's up high, you can't see on this. Getting it to move, but I'm holding it pretty firmly at my end. Make sure that shows up on the camera. Get that to stay up there. It's wiggling on the lower side here. It's tough to keep that moving the way I want. Well, nevertheless, I've got it rigidly attached here, rigidly attached to the other end, and it can move, it can have a displacement everywhere else. So I've got two rigid balls. There it is between. It's got solid hooks at each end there. Now, this means that while it can vary in between here, I'm not going to specify exactly how, it can't move here or here. That means that there must be nodes there by definition. A node at each end. Now, if I put this out, let's say this has a width L, so that at this end is positioned x equals 0, and this end is positioned x equals capital L. L just stands for length. All right. Now, when I put that requirement into my equation for the displacement of standing wave, I've got what we call boundary conditions. Boundary conditions are a general term in mathematics for what has to happen at the limits of what you're dealing with, at the edges. Sometimes these will also involve initial conditions, but in this, that's like a boundary condition in time. In this case, it's a literal boundary in space. So I impose the boundary conditions, is what that means there. That means that I've imposed it on the displacement. The displacement at x equals 0 is 0. d of x comma t. Well, t is changing over time. At x equals 0, there's a node. The displacement has to stay 0. What does that lead me to? Let's see here. Oh, yeah. So 2a sine of k times 0. So the displacement is 2a sine of kx omega, cosine of omega t. You should always know the sine and cosine of major phases. Sine of 0 is 0. Therefore, I get all of that is 0 equals 0. Check. That doesn't tell me anything useful whatsoever. But we've got a second boundary condition. The displacement at x equals L is also 0. Now let's see what happens there. I substitute in for the displacement, this equation, again, and set it equal to 0. Now, I've got 4 things multiplied by each other equals 0. I don't know everything here, but 2a, that's a constant. I can divide both sides by constants and no trouble. So that's all right. I know that either sine of KL equals 0 or the sine of omega t equals 0. Now, and it must equal 0 at all times because the node is always a node. As the wave vibrates here, the node isn't moving over any time. So this cannot be equal to 0. Because as time changes, the value of the cosine changes. This cannot be equal to 0 at all times. This, however, can be. And the amplitude can't be 0 because then there's no wave at all. I mean, the amplitude, if the amplitude were 0 all over, there's no wave at all. So that is 0. Now we do just like we did when we first found where the nodes were in a general case. If I graph out here sine as a function of theta, the generalized phase, the most general way of writing the phase, where is sine of anything equal to 0? Well, at theta equals 0, pi, 2 pi, 3 pi, integer values of pi, plus, minus, and 0. Okay, so, let's see. Sine theta equals 0, where theta equals m pi. And again, m is equal to positive, negative, 0 integers. In general, let's just deal with the non-negative ones here because they don't tell us anything extra. All right, now what is theta? It's everything inside the sine function. So that is KL equals m pi. What's the wave number k? Wave number is defined as 2 pi over lambda. And the lambda is the wavelength, is what we actually see out there. So let's put that in. So we've got 2 pi L over lambda equals m pi. Cancel out our pi. Let's solve for, let's see, we're trying to find, actually I forgot what we're trying to find right now. Oh, just formula for the general wavelengths here. That means lambda equals 2L over m. Now, because this means that m, since it's only integers, lambda is going to be only discrete values, not everything in between. So let me subscript this with an m. Lambda sub m equals 2 capital L over m, where L is the width of this We can sometimes call it the cavity, the resonant cavity. Cavity means a hole, an echo chamber. And it's allowing this resonance to take place. Resonance means where we've got these standing waves developing. So the width, the length of the resonant cavity, 2 times that over our integer m. But take a look here. Positive integer values are okay, but what if m will equal to 0? And there's an actual wavelength and all. You can't have, if I divide it by 0, I come up with infinity there. So I've got to rule out 0 because physically that doesn't work in this case. So m equals 1, 2, 3, and so on. All right, now I've got what wavelengths are allowed within an echo chamber. No, echo, it's not a sound wave, sorry. Within a resonant cavity of length L. What about the frequencies that are allowed? Let's see, what's visible? Allowed wavelengths there. Allowed frequencies. Okay. So, we know that frequency and wavelength are related. V equals lambda f. Important equation there. I want to find the frequency. So, that is V over lambda. I just pull in that equation for lambda. And I should subscript, if I'm subscripting my lambdas by specifying which, we call those values of m the modes of the vibration. So I'm going to subscript the frequency with the mode. Okay, lambda is 2L over m. So my allowed frequencies are m, the mode number, times V over 2L. Where m is 1, 2, 3, and on, etc. Since m starts with 1, look at me here. As m increases, as the number of, well, let's see here, m is also going to be the number of antinodes. You have one additional node more than antinodes. M keeps going up to positive numbers in, so the frequencies keep increasing. This is the lowest frequency. This is called, because it's the lowest, it's the fundamental frequency. And it's that there, which means that all of the other frequencies can be written as multiples m times the fundamental. It's a useful thing. If you've done any music, you may be familiar with the fundamental frequencies there from the music theory. And that's exactly what, well, this is now related to it. We'll get to acoustical sound wave standing waves in the next section. Okay, so let me draw up a sketch of what these waves look like for a few cases. Okay. So let's say I've got this open space here between the two walls of length capital L. Now, what are the different modes of the string's vibration going to look like? Now, what I'm drawing out are the upper and lower limits to the string's positions, to its displacement at any position x. So it vibrates between these two limits here. So this one is going to be for m equals 1, mode number 1. It's going to have a wavelength, lambda 1, of 2L. If you look back in your notes on the equations, lambda is 2L over m. I should write here, lambda m equals 2L over m. The frequency equals m times V over 2L. I'll box those in. So, frequency number 1 is m equals 1, V over 2L. This is called the fundamental frequency. Okay. Now, we also refer to these vibrating strings by their harmonics. M, the mode of the vibration, is also called the number of the harmonic. So this is the first harmonic. Okay, what about the second mode, the second harmonic? M equals 2. Now notice, so far the pattern is going to be correct. M is also the number of antinodes. 1 in this case, 2 in this case here. The number of nodes is m plus 1. So lambda 2 equals L, 2L over 2. Frequency number 2 equals, well, 2 times that. So it's V over L, or simply 2 times F1, and it's the second harmonic. What about the third harmonic? It takes a little practice to get this to come out in thirds. Okay, the wavelength for this one is short. Now, the wavelengths are getting shorter and shorter. There's no extra space in here. We start off with the longest wavelength we've got available. There, and now it's 2/3 of the cavity length. The frequency is 3/2 V over L, which is equal to 3 times the fundamental harmonic, fundamental frequency. And this is the third harmonic. And I'll go to m equals 4. Let me see here. Did I count this right? 1, 2. Let's see. No, that's wrong. There, okay. After I was bragging on my skills and doing it in thirds, I can't do it in quarters, which should be easier. The wavelength for the fourth harmonic is, let's see, 2 over 4L, so it's 1/2 of the cavity length there. Frequency is equal to 2 times V over L, which is equal to 4 times the fundamental frequency, and that's the fourth harmonic. So, look here. This is a complete wavelength in this case. This is half a wavelength here that we're seeing, and so on like that. This is a wavelength and a half, and so on. So what? Okay. M is the number of antinodes. 1, 1, 2, 1, 2, 3, 1, 2, 3, 4. And M plus 1 is the number of nodes. 2 of them here, 1, 2, 3 here, 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay. The rules here apply to transverse waves. That means vibrating strings, ocean waves, light waves as well. I won't go through the separate calculations for light waves, although the book has examples. But the math works out to be the same. But the wavelengths for light, for visible light, are much shorter than this. So the number of modes you can get in a given reflective cavity are much larger.